Previously, we have looked at an estimated ACF and an estimated PACF for an observed time series, and we've talked about how one could use those plots of the corresponding functions to choose particular candidate models to examine further. Now, the purpose of this section here is to go through the steps of model building, where we include looking at these estimated ACF and PACF to choose candidate models, and now we talk about how we can choose between these models through this model building process. Now, model building is a common topic that you will find in many STAT courses. Each STAT course typically that you take, you often talk about a certain kind of data, certain kind of models associated with it. And so because of that, then you talk about how can we model build, meaning decide what goes in the model, what comes out of the model, and how to choose between particular types of models. And typically a number of steps are given to do the process. So if you've had courses like that, you will notice some similarities between what you've learned in those other courses to what we're doing here in terms of our steps. But there's going to be a lot of differences still, because this is a different type of data that most likely you've seen in another course. And we obviously have different kinds of models as well. Okay, so in total, there are going to be 6 different steps to do model building and eventually come to one overall model that we're going to use for our time series data. Here's steps 1 through 3, and you're going to see some similarities to what we've done in the past, at least with these first 3 steps. So step 1, we're simply going to plot our data. Construct a plot of x of t versus t. Also plot the estimated ACF. In this step, the purpose of doing these plots is to check for non-stationarity. So we check, is there non-stationarity in the variance? And how do we do that? Well, we look at this plot of x of t versus t, and we look to see for different, let's say, large time, sets of time points, is the variability in the data different? Also, we check for, is there non-stationarity in the mean? And again, how do we do that? Well, we look at a plot of x of t versus t, and we look to see for a certain segment of time, does it look like perhaps the true mean is different for a large segment of time versus another large segment of time? If it is, then we have non-stationarity in the mean. Also, with the estimated ACF, what we look for is very large and absolute value estimated autocorrelations. And if you see that, then that suggests that you do have non-stationarity in the mean. And once we see that we have non-stationarity in the variance or the mean, we make changes like we've talked about before. Maybe use a log transformation to try to deal with the variance issue, use differences to try to deal with the mean issue, and then we construct the same kinds of plots again now for our transformed data to see if our resolutions worked. Then step 2 of the model building process is construct plots of the estimated ACF and PACF of the approximately stationary time series. Let's just simply call it x of t, even if we've made some kind of transformation of it. And then what we try to do is we match patterns that we see in these plots with what we would expect would occur for a particular ARIMA model. And so we've talked about in the past about you look to see, does an estimated ACF or PACF cut off to 0, or does it perhaps tail off to 0? And that kind of information then leads to choosing, well, do I use a p equal 1 or p equal 2 or q equal 1, q equal 2 for our ARIMA model? And from that, you might get a number of different candidate models to examine further. Then with these particular models, you go to step number 3 and you estimate them using maximum likelihood. Okay, so let's take a look at an example in a familiar setting. We're going to work with this data that's been simulated from an AR1 once again. So step 1, we do a plot of the data. Well, first of all, we need to read the data into R, then we do the plot of the data as we've seen before. And so again, what I'm looking for in this plot is non-stationarity in the variance, non-stationarity in the mean. Now, remember, since the data is actually simulated from an AR1, we do have stationarity. And so what I'm looking for in this plot is that, well, looks like the true mean is approximately the same over time. I'm also looking to see, is there a large amount of variability over a significant number of values of t, and I don't see that. And you might be looking, well, hey, take a look at that. We see some larger variability for this segment. Well, yeah, we do, but you can't be too picky. I guess that's a non-statistical way to put it. That, don't look for trends where the trends don't exist. Remember, this data does come from an AR1 that does have stationarity. So having this extra variability for a small segment like this is not something to worry about. Now, when would I be worried? Well, here's a plot of our data. Let's say, here's time, here's x of t. Now, if I see something like this, suppose that this is my time series. That's a dramatic example of having non-stationarity in the variance. In that particular case, I would be concerned, and I would try to look at some transformations to resolve the problem. Now here's the estimated ACF, and whenever I do an ACF, I always do a PACF. So really, we don't want to even look at that at this particular stage of our model building process, but I always produce both of them at the same time. And so with this estimated ACF, we don't have like any extremely large autocorrelations that last for a significant number of lags. So therefore, I don't have concern about non-stationarity in the mean from this plot of the ACF. Okay, so in step number 2, then we choose particular candidate models from what we see in the estimated ACF and PACF, and that's why I did do the PACF plot here. So for AR1, the characteristics would be the PACF cuts off to 0 after lag 1. I'll take a look at this. Here's lag 1, and it essentially does cut off to 0. Remember, these dashed lines are drawn at plus or minus 1.96 divided by the square root of n. Anything outside there, it gives you evidence that indeed a partial autocorrelation is different from 0. But what we have here is all the partial autocorrelations are within those limits. So after lag 1, we do not have sufficient evidence to indicate that we have a non-zero partial autocorrelation. Only does it occur at lag 1. Also for AR1, we would expect the autocorrelation function to tail off to 0. Now note the way that I actually drew the autocorrelation function this time is I actually started at lag 1 versus lag 0. And so what we do see here is we do have a tailing off, and it's not unusual to have this oscillating pattern through the plot like that. Notice how they're all within those plus or minus 1.96 divided by square root of n limits. But having an oscillating pattern like that is completely normal. The key is that they're all the autocorrelations are fairly close to 0. So this indicates that, yeah, an AR1 would be appropriate. Now let's think about a different way to approach this. Let me do a little bit of erasing. If we didn't know that indeed the data came from an AR1, you might be thinking, okay, look at this right here. I have a significant autocorrelation at lag 1 there. And maybe even at lag 2. Well, I do have it at lag 2. I have it at lag 2 there. So you might be thinking, okay, maybe this tells me MA2. Now, of course, though, the partial autocorrelation function should be tailing off to 0. It doesn't really look like that there, but you know, in actuality, when you don't know what the data is, where it comes from, you know, it can be difficult in making decisions about what to look at in terms of these candidate models. So, at the very least, how about we actually take a look at a moving average 1 and see what happens with that model in the next step of our model building process. Okay. So step number 3, we estimate the model. Here's our AR1. Again, phi hat 1, mu hat. Now, once again, the data was simulated from an AR1 with mu equals 0. But if I didn't know that to begin with, I would always still include .mean equal true so that I still get an estimate for mu. Now, we could also do some, while this is done actually in the next step, we could also do some coding here to get a hypothesis test for whether or not phi 1 or mu 1 is equal to 0 or not. And so to do this here's my coding. Somewhat similar to what we had before, but a little bit different. So I have my test statistic z here. And I pull out the conf component of mod.fit1. This contains phi hat 1 and mu hat together. Then what I also do is I go to my estimated covariance matrix. I pull off the diagonal elements of that covariance matrix. So this is what the covariance matrix will look like real quick here. So the diagonal element would be the 1, 1 element, the 2, 2 element. I pull those off of that matrix using the diag argument. I take the square root of that as well, so I can get the standard deviation, in other words, the standard error. And so because of how R does its calculations, it's going to match up when it does the division here. It's going to match up phi hat 1 with the square root of the estimated variance of phi hat 1. Then it's going to take mu hat divided by the square root of the estimated variance of mu hat, because of how R does vector-based calculations by element. So now Z is going to be a vector that has a length of 2 that contains the 2 test statistics that I want. Then I can use the p-norm function with them to find the p-values for each of the corresponding test statistics. And here is the corresponding output from that. And we can see for phi 1, there is sufficient evidence to indicate that it does not equal 0 because I have extremely low p-value. For mu itself, I have a somewhat of a large p-value, 0.23. So there is not sufficient evidence to indicate that mu is different from 0. This is what we would expect because we know in this particular problem, indeed, mu is truly equal to 0. However, this doesn't mean then that I remove estimating this mean from the model itself. I still keep it in there for a number of reasons. First, of course, just because you don't reject HO, that doesn't mean that, in this case, mu is truly equal to 0 from the hypothesis test, because you can never conclude that the null hypothesis is true with a hypothesis test. But second, this also corresponds to what you would see in a regression setting. perhaps we have a model that looks like this. The expected value of y is equal to beta 0 plus beta 1 times x. If you did a hypothesis test for is beta sub 0, is that equal to 0 or not? If you don't reject HO, you don't remove the y-intercept from the model. You just simply keep it in there. And we will do a similar thing here with respect to mu. Okay. Now, here's my moving average 2. I'm going to put the results into mod.fit2. This is what we get here. Here is theta hat 1. Here is mu hat. So notice I'm still estimating what that mean is. So if I were to write out my model, it would be x of t is equal to negative 0.4794 plus 0.58 times w, t minus 1 plus wt. So that's what the moving average 1 model would look like. I can do my hypothesis test just like I did above. Notice the moving average corresponding parameter for theta 1, there is sufficient evidence to indicate that it does not equal 0. That's interesting. Also take a look at mu itself. There is marginal evidence that it's not equal to 0. That alone, though, does not mean necessarily, though, that that is a good model to choose, as we will see shortly. Okay, so we've done steps 1 through 3. Next, let's do step 4, the model building process. For each model chosen, we are going to investigate various diagnostic measures for it. What that basically means is that we want to make sure that the corresponding assumptions, mathematical assumptions that we have with our model are actually satisfied. So the first thing that we're going to do is take a look at this white noise assumption. We assume that the WT are independent with a mean of 0, variance of sigma squared W. In other words, white noise. We want to check to see if that is actually true. And so while we don't observe WT directly, we can get the corresponding residuals that we've discussed before from our model's fit. And using these residuals, we can examine, well, this assumption of white noise. How do we do that? Well, we look at the estimated ACF plot of these residuals, and based upon what our knowledge is in the past of an autocorrelation function plot, we use that to make a decision of, okay, does it look like now what's left over from the model's fit is that white noise? If the plot looks okay, what do I mean by that? Well, again, here's, let's say, our plot. We have lag H. We have the autocorrelations. Let's call them rho sub E, rho hat sub E H, where E's, we commonly use E to mean residuals, even though at least how we state our model, we call it W. I'm just going to use E for that to differentiate it from the other autocorrelations for the original data itself. And let's say we have these dashed lines across corresponding to our hypothesis test. And if we have autocorrelations that maybe look like this, all the autocorrelations from the residuals are within those dashed lines. Hey, I'm okay then with that assumption of the WT is truly now white noise with our corresponding model. Now, if though, from looking at the ACF, maybe you have something like this, where you have some of these autocorrelations that are outside those dashed lines, then that would tell me, uh-oh, there is a problem with this model, because these residuals should look very similar to what we would expect for white noise in terms of the autocorrelations. So what that tells me then is that changes need to be made to my model because my model is not doing a good job. Now, well, what changes do you make? The changes correspond to the autocorrelations of the ACF. Similar to when we were looking at an ACF plot of x of t itself, and when we look for patterns in that plot, we are going to do the same thing here. And those patterns will tell us what changes need to be made to the plot. Made to the model. More on that shortly. We also can do the same thing with respect to the partial autocorrelation function. So do a plot of partial autocorrelation function now for the residuals, and again look for patterns. If there's patterns, that suggests changes need to be made to the model. If there are not patterns, meaning also, let's say all the partial autocorrelations are within those dashed lines there, then you're good to go, at least with respect to this diagnostic aspect. Okay, so let's talk about this a little bit more then. Let's say that we have the following model. We have our AR operator, and I'm going for emphasis, I'm going to put the corresponding order of the AR operator, meaning the number of fees. We're going to call that P prime. We have the differencing part of our component, where again I'm going to use D prime to represent the number of the differencing order. We have X of t. We have the moving average operator as well. It has an order of Q prime. And rather than having WT there, I'm going to use B sub t, where this B sub t is going to play the same role as we would normally have for WT, but B sub t here is not necessarily our white noise. Now let's say we did a residual ACF and PACF of the corresponding estimates for B sub t from using that previous model. And from looking at the patterns in the ACF and PACF plot of these residuals and interpreting those patterns basically in the same way as we had done previously when we did an ACF plot and PACF plot of the X of t. Suppose now for these residuals, I have this corresponding model where I have an AR operator, and I just put a line on top of this to help distinguish it from the previous AR operator that we had. This AR operator is for the residuals from the previous model. It has an order of, let's say, P double prime. I have the differencing. I have a moving average operator as well for these corresponding residuals. And let's say that this model then completely takes care of the problems that we found with the previous model, so that we do have white noise actually left over. Okay. So if we go back to our previous model then, and let's say we solve for B sub t, so that we only have B sub t on one side of our model. Notice how B sub t is there too, because we're doing a model now for B sub t essentially directly, since we're working with the residuals. Suppose we solve, suppose with, let's see now, with model 2, we solve for B sub t. This is what we get. Notice how this is written in terms of W sub t. And let's put this term now into our first model, model 1, for where we saw B sub t. We do a little bit of algebra, and this is what then we get. Now our model does have WT in it, and one could actually multiply out these two AR components, these two moving average components, or operators, and to get one overall AR operator and one overall MA operator, and then that's your model. So the purpose of this kind of abstract demonstration here is to show you that basically we're putting the components together of our original, let's say, candidate model with now this new model based upon the residuals, and that's how we get our overall ARIMA model. To help see this a little bit better, let's actually put some numbers here in terms of, for these symbols. So let's say originally a candidate model has been identified. It's a moving average 1 model. I'm sorry, it's an ARIMA 011 model. And let's say that the model, and this is actually an incorrect model. We have come up with this particular model here. Somehow, let's say we know what the true value of theta 1 is, just that for demonstration purposes. And notice we have these B sub t's. From that model, we do a residual ACF, a residual PACF, and based upon how we know to interpret those functions, we then identify for the residuals themselves a new model, an MA1 model, then that looks like this, and somehow we know what that corresponding theta is, let's say. Okay, so what we can do now is take this B sub t and put it into that previous model. And also I should say this second model does handle any problems that were found, so that we do have white noise in the end. And so what we do is, where we saw B sub t before, we plug that in to our original model. We do a little bit of algebra, and look what we get here. We get now an ARIMA 012 model. And so what this basically means is, when you look at that residual ACF and PACF, what that's telling you is that any Q, any P that you get essentially is going to be added to what you had originally identified as a candidate model before. That's how the residual ACF and PACF is used, and how it's extremely useful to fine-tune a particular model to get a model that will work. Okay. Now, let's take a look at another aspect to this diagnostics. We can examine the standardized residuals for outliers. So the standardized residuals here, let's call them E sub t, is just simply take your X sub t times its corresponding predicted value that we've seen previously, divided by the square root of the corresponding, the square root of the estimated variance of that difference. In other words, the forecast error. This estimated variance for the forecast error just ends up being sigma hat squared w. So when we take the square root of it, we have just sigma hat sub w, and then we have the forecast error above. And so what we're going to do is treat these standardized residuals as approximately a standard normal. Again, in another class, typically in a regression class, you did something very similar to this, where you find the standardized residuals and you compare them to like a standard normal, in terms of like the quantiles from a standard normal, and from that you make judgments about, do I have any unusual observations that are not being fitted well by the model. So we're using that standard normal approximation, then we would expect about 95% of these standardized residuals to be within plus or minus 1.96, or let's just say 2. We would expect about 99% of them to fall within about plus or minus 3. So, we have to be, now, let me back up. So for standardized residuals falling outside these ranges, those perhaps could be outliers, indicating that there's a problem with the model's fit. Now you got to be careful with using this here, because notice, let's say n is 100. And let's say all the residuals are essentially are okay. Now, 95% of them should fall within plus or minus 2. So that means about 5% of them should fall outside of plus or minus 2, which means that we would expect on average about 5 that would be outside of plus or minus 2. And as long as they're not too far outside, hey, that's okay. Your model's fine. Similarly, with that 99% threshold, or corresponding to plus or minus 3, you would expect, if you have a sample size of 100, about one of them will fall outside of the plus or minus 3. As long as it's not too far out, you should be fine. But, where should you be worried? Let's say you have, 10, maybe 15 of your standardized residuals that are outside or plus or minus 2. Well, then that will tell you, hey, that's kind of unusual. I wouldn't necessarily expect that. If I have, let's say, 5 or 10 or 15 outside of plus or minus 3 when I have n equal 100, well, then that is unusual. If also, let's say that I have, one of my 100 standardized residuals ends up being 10. Well, yeah. If you only have one that's outside of plus or minus 2 or one outside of plus or minus 3, that's usually not alarming. But given the size of that is alarming, because it would be extremely unusual to have an observed value of 10 if you were to, let's say, simulate data from a standard normal with a sample size of 100. So how do we handle these situations? Well, look at different models. Maybe different models don't have those same kinds of standardized residuals. If, however, that still doesn't work, there are additional terms that can be added to a time series model to specifically account for maybe situations like this. You could use what are called special forms of what are called transfer function models, which obviously we have not talked about yet. Okay. Now, so let's look at another diagnostic tool. Plot the standardized residuals versus time. Simply, your plot's going to look something like this. Let's see here. Here's time. Here's the standardized residuals, or you could just do residuals themselves. And if through time, you have something like this, and then all of a sudden it goes down like this and then comes back up. Well, that's kind of strange to see, because these standardized residuals essentially should be similar to white noise, so they shouldn't have any dependence on it. But we do see something. If we do see something like this, this tells us then the model's not capturing something. There's still some autocorrelation in there that we wouldn't expect given our particular model. So that suggests try a different kind of model. Another diagnostic tool is to perform a Jungbox Pierce test. And this again looks at the assumption that WT is now independent. So what it does is simply this particular hypothesis test. So let's say that our autocorrelations for our residuals that we get are denoted again by rho sub e. And we look at the autocorrelation at lag 1, lag 2, up to, let's say, lag capital H, just to be general. And we're essentially doing an overall test. We're checking in the null hypothesis, they're all equal to 0, versus in the alternative, at least one is not equal to 0. And so what this test ends up doing is, for a large number of lags, and very often the way that this is actually implemented, you might try, let's say, h equal 1, h equal 2, h equal 3, all the way up to, it's customary to go up to about 20. So you end up doing 20 different hypothesis tests, where each of them is looking at one autocorrelation, the first two autocorrelations, the first three autocorrelations, so on. And you want to make sure that indeed you don't reject HO. If you reject HO, that says there is a problem in your model. You still have some dependence that has not been accounted for with the model itself. The actual test statistic, and we're not going to go through a derivation of it, the test statistic is often referred to as Q in practice. This has nothing to do with how we've used the letter Q in the past. And you simply take your sample size times the sample size plus 2, and you sum over all your autocorrelations for the residuals up to lag H. You take your autocorrelations, you square them, you divide by n minus H. Under the null hypothesis that there is no autocorrelation up to lag H, Q has an approximate chi-squared distribution with H, capital H minus P minus Q degrees of freedom for a large sample size. If Q is larger than, let's say, the 1 minus alpha quantile from this chi-squared distribution, then you reject HO. You shouldn't use that model. If Q, though, is less than or equal to this corresponding quantile, hey, it looks like your model's probably okay. You know, this isn't a guarantee, but obviously if your model was okay, you would want to say don't reject HO. Now, to actually implement the test, there is a function in R called box.test that will allow you to do it. We won't use that necessarily directly. There's actually another function that we will use to do it, but I just want to bring it up because some people will use it. Also, there's another version of this test statistic, an earlier version that just has Box and Pierce, their name on it. This is what the test statistic looks like, and it works in a very similar manner. We will just use the Jungbox Pierce test, but again, I just wanted to bring this up because some people will use this other tests. Now, the function that we will use to automatically calculate this test statistic for us is called TS-diag. This stands for Times Series Diagnostics. This functions in the stats package of R. Okay, another diagnostic tool that we're going to look at is we're going to examine the normality assumption for the WT. So to do maximum likelihood estimation, we need to assume a normal distribution. And so we can use usual methods. Now with the residuals or the standardized residuals, either will work just fine to check for normality. The usual methods that people use to check normality, I expect all of you have used simply a histogram before. So, if our histogram here, the standardized residuals, looks something like this, mound shaped, symmetric. You could actually even plot a normal distribution on top of it. If that looks nice, okay, yeah, there's not sufficient evidence against a normality for me to be worried. Another standard tool is a QQ plot. Note that this Q here has nothing to do with the Q for the Jungbox Pierce test. The Q here stands for quantile. So a quantile plot. This is a common tool, but I wouldn't be surprised if some people viewing this video have not heard about it before. So let me just really briefly describe it. It's very easy to interpret. Let's see here. Let me pull up another window so that I can write on. Hold on, this open up in a different monitor. Okay. So imagine, let's say that we had n equal 100. Okay. So we have 100 observations and we were able to come up with 100 residuals. And so with these residuals, let's say we order them from smallest to largest. Oops, I can't count. Okay. So here is the smallest residual. Here is the largest residual. Okay. Now, so these are my residuals. Let's also find quantiles from a standard normal. And let's say this is the first quantile that we're going to find 100 different quantiles. Okay. What quantiles are we going to have? So we have 100 observations in our time series data set. So what I'm going to do is find the 1 over 101 quantile, the 2 over 101 quantile, all the way down to the 99 over 101 quantile, and the 100 over 101 quantile. Okay, and let's also say that these are standardized residuals. This would just make this description here easier, even though you don't need to. Okay, now, why did I use 101 there? Well, because otherwise, if I just simply use 100, I would have 100 over 100, that quantile, which would simply be positive infinity. I don't want that. So I'm going to, that's why I chose a number that was 1 greater than the actual sample size. And so anyway, for example, I could use the Q norm function to find this. I would say Q norm P equal 1 over 101, mean equals 0, standard deviation equal 1. Now, if these residuals approximately follow a standard normal distribution for standardized residuals, I would expect this standardized residual here to be about the same as the actual standardized residual there. Similarly, standardized residual here would be about the same as the one that was located there all the way up to the 100th. They should be approximately the same. And so what that means then, if I were to do a plot of the standard normal quantiles on the x-axis, the standardized residuals on the y-axis, what I would expect is that, let me actually draw this, let's see now. We'll put -3, -2, -1, 0, +1, +2, and I'm running out of room here, +3, sorry, it's not the best drawing here. What I would expect is that if I have a standard normal quantile of approximately -3, I would expect the standardized residual, that corresponding ordered one, to be about -3 as well, similar for -2, and so on. So that basically I would have a 45-degree line drawn from approximately, well, here's where the origin would be, right there. Drawn out from the origin. And I would expect, when I were to plot these 100 standardized residuals versus their corresponding standard normal quantiles, I would expect them to all be approximately around the line. Will they be exactly? No. You're going to have a little bit of deviation from the line, but there shouldn't be too much. If that were to happen, then that says, hey, my standardized residuals are matching up well with a standardized normal distribution, so my normal distribution assumption is satisfied. If instead I have something that looks like this, so ignore the dots up there, let's say my points are now looking like that, where what this is saying is I have some deviation in the right tail of my standard normal distribution, and therefore my assumption of normality for my original data is not satisfied. So that's how you handle this. You're looking for larger deviations. Now, as I said here, you don't have to have a standardized residual. It could be just a regular old residual. In fact, that's what we're going to use. You can still plot them against the quantiles from the standard normal. It's just this line, which actually will end up being automatically drawn for us, is not going to be a 45-degree angle from the origin. It's going to be a little bit different. But again, what you're looking for are the points corresponding to the line. Okay. So we use a QQ plot, we use a histogram. And then lastly, perform hypothesis tests for the corresponding parameters in your model. If you are having, we want to have, a significant, we want to have significance here in terms of we want to reject HO. If I don't reject HO, while that doesn't necessarily mean that, let's say, a phi or theta are truly equal to 0, but that should start calling into question of, okay, if that phi, let's say my p-value is 0.5 for testing phi 1 equal to 0 versus not equal to 0, that tells me, wait a second here, do I really think that phi 1 should be actually in the model? It's not a definite answer, yes or no, but it should at least start calling into question about if the model that you chose is a good model to use. Okay. Those are the diagnostic tools that we had to look at. Obviously, there's a lot of them, and it will often take time to actually go through these tools. So let's do this with the example here then. So we're going to go back to the AR1. We're going to do this step number 4. The first thing that we're going to do is use this function tsdiag with the AR1 model that was saved in mod.fit1. I'm going to do my Jungbox Pierce test up to lag 20. That's what the GOF.lag stands for, or corresponds to. GOF stands for goodness of fit. Again, you could use a different function for it too. So the tsdiag is going to give us a number of different things. Let me make this a little bit bigger here. So the first thing that's going to give us is a plot of the standardized residuals versus time. And so what we're looking for here is, are there any outliers? And so what we can see here is, we have about time point, about 48. We have a value that's about negative 2.3. We have a value at 100 that's maybe about positive 2.1. Excuse me. We have another one here that's a little bit outside of negative 2, but pretty much everything else is within plus or minus 1.96. Again, when we have a sample size of 100, and we're using plus or minus 1.96 or plus or minus 2, we would expect about 5% of these standardized residuals to be outside of the plus or minus 2. And, we have about 3, maybe 4 that are outside. So this is not unusual. Also, they're not too far outside of plus or minus 2. But so from this, I can conclude, yeah, it doesn't look like there's any outliers. Also, what I'm looking for in this particular plot is, are there maybe some trends that we're having in these residuals? And the way that the plot's drawn, those trends can be evident about by comparing everything to 0. So, sorry, I should have mentioned this at the very beginning. So we have these lines that are drawn out from 0. These correspond to the standardized residuals with respect to time. So again here, for at time 1, we have a value of approximately about 0.2, positive 0.2. And at time 100, we have a value of about positive 2.1. Okay, so we have these lines representing the residuals that are drawn out from the zeros. And the reason why that's done is to help you see patterns or trends over time by looking at, okay, do I have a large number of maybe standardized residuals that are all positive? Maybe I have large ones that are all possibly all negative as well. And if I see that, that says that I might have some dependence that's left in these residuals that I don't want to have. I don't have these residuals being white noise. And so what we see here is that we don't really see any trends like that. And I'm looking for larger trends. The closest is maybe right here, where we have about 6 in a row that are all positive. But it's really not too bad. And here I have a few as well. But we're looking for larger trends than necessarily that. So from this, I don't think I really necessarily have really issues with respect to this particular plot. Now we also look at the ACF of the residuals as well. This is automatically produced by tsdiag. Unfortunately, this starts at lag 0 there. So again, we do not look at that very first value there. We have these dashed lines drawn at plus or minus 1.96 divided by the square root of 100 for us. Autocorrelations outside of this range indicate that there's evidence that it's not equal to 0, that autocorrelation. And, looking over here, it looks like everything's fine. Maybe just at lag 5, we have a marginal significance there. But otherwise, everything is looking pretty good. Then we have the Jungbox Pierce tests. Unfortunately, I guess R decides to drop off Pierce and just do Jungbox. What we have here is we have the lag on the x-axis, like what we would have for an ACF plot. On the y-axis, we have the corresponding p-value for doing a hypothesis test. This is lag 1. This is simply doing the hypothesis test of rho of E1. Is that equal to 0 versus not equal to 0? We have a p-value about 0.4, indicating that there's not sufficient evidence to indicate that we have non-zero correlation, which is what we want. Let's take a look at another one. Let's go out to lag 15. What this is representing now is rho of E, or rho sub E of 1 is equal to, we go all the way out to 15. So we have the first 15 autocorrelations. We're testing, are they equal to 0 versus not all equal 0. Excuse me. We have a p-value again of approximately 0.4, and again that's what we want for this particular model. And we can see overall, this line also is drawn at 0.05. We see overall we don't have any small p-values for going all the way up to lag 20. This is what we want to have happen if we want to use this particular model. You know, we are kind of getting close around lag 5, and notice how that kind of corresponds to once we include lag 5, that autocorrelation into it. And remember, this was just for lag 5, the hypothesis just for that lag 5. This is a hypothesis test for lag 1 through lag 5. But we can see what's happening there. We can see its effect here. It lowered the p-value. And this remains a little bit lower, the p-value, after that as well. Okay. Let me zoom back out. So overall, things are looking good. You know, maybe we have something going on at lag 5, but it's really not too bad. Next, we can do now a partial autocorrelation plot of the corresponding residuals. And look at this. All the observed partial autocorrelations are within our blue dashed lines there. So that is great. This is indicating that the model is looking good here. We can also do a plot of the histogram of the corresponding residuals. Unfortunately, my line here got a little bit cut off. And so for this particular plot, I just simply do a plot of the residuals, and then I put a normal distribution approximation upon it. Let me actually go back and show you the corresponding code. So first of all, to do that second set of plots, I made a frame, a 2x2 frame, so I can insert the plots into the frame. It's going by row. So the first row, first column is the PACF. The first row, second column is the histogram of the residuals, and I simply pull out the residuals as we've done before from mod.fit1. Now, something that I'm also doing here that perhaps you may not have seen before, I do freq equal false here. What that corresponds to is the y-axis. I don't want the y-axis to be the frequencies as you would normally have for a normal distribution. Instead, R is going to rescale the y-axis so that I could plot on that exact same y-axis the corresponding normal distribution. So it rescales it to the density scale. If you're not familiar with how to do that or what's actually involved with that, just let me know and I can talk about that. Now to plot then the corresponding normal distribution on it, I use the curve function. And what curve is going to do is for on the plot itself, it's going to see where the minimum and the maximum is. It's going to find by default 101 equally spaced values corresponding to that x-axis minimum and maximum. And it's going to plug that in here for x, where for my EXPR argument, which stands for expression, I'm going to plot the density of the normal distribution. In other words, what we normally think of as f of x in a mathematical statistics course. And I'm going to plot the density of the normal distribution. I'm going to evaluate it at these equally spaced x values. This has to be the letter x there for the curve function to work. And what's the mean of my normal distribution? Well, how about we just use the mean of the residuals? What's the standard deviation of my normal distribution? Well, the standard deviation of those residuals. It seems like a reasonable thing to have happen because we're checking for normality. I don't care what the mean is. I don't care what the standard deviation is. I just want to know, does this fit a normal distribution? The color of the line that's going to be drawn is red. I'm going to add that then to the previous plot. And so this is then what we get. And we can see that this normal distribution plotted seems to follow a similar shape to the height of the histogram bars, indicating that, yeah, it looks like we have normality satisfied. Now to do the QQ plot, this is now going to go into row 2, column 1. I can use the QQ norm function. What do I want to do the QQ plot of? Well, my residuals. Put a nice little label on the y-axis, also put some nice grid lines on there. And then, as we talked about before, there's typically a line drawn that helps you see, well, where should the residuals match up with the corresponding quantiles from the normal distribution. To draw that line properly, I can use the QQ line function. It automatically scales everything properly. And to tell R, okay, we're working with these residuals, I need to put the residuals in there again. And so this is what we get. So the QQ line function put the red line there. So we have the residuals here, and we have what would be the corresponding quantiles from a normal distribution. And what we're looking for here, so for example, the smallest residual is approximately about a little bit greater than -3. That corresponding quantile from the standard from this normal distribution would be about about 2.7 or so. Similarly, the largest residual was about 2.2, and the corresponding quantile will be about 2.5 from the normal distribution. We're looking for are the points on the red line. They're not exactly, but they're very close to it. So I'm satisfied with normality. This is going to agree with what we see for the histogram. Now again, if I were to see something that looks like this in the plot, or maybe like this, and you can do the same thing down there, then I would be alarmed. Okay, so this AR1 model is looking pretty good. What if we did the MA1 model now? So we use the tsdiag function once again. Here's my plot of my standardized residuals. Relative to the y-axis here, we don't seem to be having really too many things outside of plus or minus 1.96. Maybe just a little bit more than what we had before, roughly, but it's nothing alarming. I don't know, maybe I'm biased because I know what the correct model is. I am starting to see maybe more sets of these standardized residuals that are positive or negative. Perhaps I'm looking into it too much. I wouldn't make a formal judgment alone based upon what I see, but rather what I would do is focus more now, or at least I'd be more suspicious then, and so that when I come down to this plot of the ACF of the residuals, again, we don't look at that one. Take a look at this. We do have a significant autocorrelation at lag 1 for the residuals, maybe marginally significant at lag 2. Otherwise, not too bad. Look at the Jungbox Pierce test. Look at these p-values. These p-values are all small. This is a warning signal then for us. It looks like we do have some leftover autocorrelation remaining in our residuals that we shouldn't have if we wanted to use this model. So some of the model's assumptions appear to be violated based upon what we see here. So I can do now these other plots. Look at the partial autocorrelation function plot for these residuals. Again, lag 2. I have a significant value there, marginally at lag 1. You know, the histogram's not too bad. The QQ plot's not too bad. I mean, we got a little bit there, but not too much. You know, and I should have mentioned this before. I apologize, I didn't. You know, if you are worried about the normal distribution assumption, well, what can you do? Well, you can try similar transformations as what one could do if you have non-constant variance, that, you know, problems with the non-stationarity of the variance. You know, like a log transformation can often be very helpful to satisfy or to take care of the non-normality issue. So that's the number one thing that you can do without going to, let's say, more exotic models that could be available to us. Okay, so here are some notes. So with the AR1 model, we have like a partial autocorrelation that's marginally significant at lag 5. Some people would say, okay, why don't you add to your model now another term for phi sub 5 times x of t minus 5. You know, we haven't talked about how to exactly do that. We will get to that, but we haven't talked about how to do that yet. And some people say, okay, well, maybe you should try that. Excuse me. I prefer not to do that. To, let's say, skip ahead like that from from going from phi 1 to phi 5. I would first look at some of these phis beforehand and continue in an order from phi 2, phi 3, phi 4 before I would get to lag 5. Just due to the modeling approach, it's a reasonable thing to do that. Because if you have it at lag 5, I'm sorry, phi 5, why don't you have that autocorrelation at lag 2, 3, and 4? Now, there are situations where I would definitely look at that, but that's not unless, or the only situation typically that I would ever consider that for, is if I have some kind of seasonality component to my data. Like perhaps let's say maybe it was lag 4 instead. Maybe I have quarterly data. It would not be unusual then to have a significant autocorrelation at lag 4 if you were not accounting for that quarterliness in the data. Later in our course, we will talk about those kinds of models to handle that kind of situation. But until then, I typically would not consider doing something like this. Now, a similar thing could be said too we had a marginally significant autocorrelation at lag 5. And so perhaps now maybe you could look at a moving average component corresponding to theta sub 5. Again, I typically would not do that unless I had some definite need for seasonality. Okay, some other notes here. Let's see. So yeah, I talked about the autocorrelation. We do have problems with the MA1 model. So alone, this MA1 model should not be examined further in the model building process. You might have to make some changes to that corresponding model. We talked about the hypothesis tests for the parameters as well. With these particular hypothesis tests, it just gives the test statistics out formally. We would reject HO. If I did not reject HO, then that would call into question, well, do I really need like a theta 1 term? We also talked about the Jungbox test. You know, the MA1 model itself does fail the Jungbox test. So let me come back up here. There's one other thing that I wanted to mention. So, you know, with respect to the moving average 1 model, if I didn't necessarily want to give up on it and I wanted to look for potential changes to that model, what I would do is, let me do a little bit of erasing to clear some stuff up here. I would look at the ACF plot of the residuals, and I would look at the ACF plot, I would also look at the PACF plot of the residuals as well, and let that guide me to choosing particular terms to add to the model. So, the problem is, well, which terms do I use? Well, because I have a significant value at lag 1 for the PACF and also lag 2 for the PACF, I would start considering to add to the model autoregressive terms. Start with a phi 1, start with a phi 2. Look to see if this handles then the corresponding problem that we see. In a similar manner, I would do the same thing here with respect to moving average. Maybe now, since at lag 1 I have a marginally significant autocorrelation, now maybe I need a theta 2, or I need to have a q equal 2 overall for my moving average, maybe q equal 3. Now notice here, though, with both of these plots, it's difficult to see, let's say, a tailing off to 0 here, and this can happen. But in the end, it doesn't hurt to just try to add these terms to the model and see what happens. Maybe then, after you redo these diagnostics, you find out, oh, okay, this has improved the model. Now I do have white noise that appears to be left over. Maybe my Jungbox Pierce test p-values now are all large. And so that's how this model building process can be an iterative process to follow. In this case, though, we do see an AR1 model seems to fit well. So I'm okay with, moving on and going on to the next step as is for that particular model. Okay. So this now takes us to step 5 of the model building process. So for each model that makes it through 4, and including any changes that you made to a particular model, pick the best model based upon model parsimony and the AIC. The best model then corresponds to the one with the smallest number of AR parameters and MA parameters and the smallest AIC. Okay. So what does this mean? Well, I still remember back to one of my classes from my very first year of graduate school. The professor who ended up actually becoming my advisor, I was teaching regression analysis to our class, and he was talking about how one should always look for the model that is the most parsimonious, but yet best predicts the response variable. And that's what this step 5 is essentially addressing. Parsimony means smallest number of parameters that you need, but yet still is going to do a good prediction. And so the way that we measure this is, again, look at the number of parameters that you have. So if I had a choice between an AR1 model versus an AR10 model, and based upon the diagnostics, they both seem to predict do well in terms of satisfy the assumptions of the modeling process, I would pick the AR1 model. Also, with the Keki's information criterion, this is a common tool used to evaluate how well is this model doing. And I understand that maybe some of you have not seen it before, so I'm going to give a brief introduction to what a Keki's information criterion is, or AIC for short. In the end, to have in the back of your mind, the model with the smallest AIC is the best model, according to this particular criteria. So this is what how the AICs is formed. So numerical value. You take -2 times your log likelihood function, evaluated at your parameter estimates, plus 2 times the number of parameters that you're estimating. Okay, so why are we using this this value as a way to evaluate our model? Okay, now this all goes back to basics about likelihood functions that you would see in a mathematical statistics course. A likelihood function measures the plausibility of your set of parameter estimates, or corresponding model then, because you have parameters corresponding to your model. And when we find the maximum likelihood estimates, we want to find the possible values of your parameters that make that likelihood function as large as possible. Equivalently, make that log likelihood function as large as possible. The values for your parameters that make it as large as possible are essentially now the most plausible values to have for your parameters given your observed data. And thus, these are called the maximum likelihood estimates. So it makes sense to, let's say, evaluate an overall model's fit by how large is your log likelihood function, especially if you want to compare it to maybe log likelihood functions from other models. And so we want this log likelihood function to be as large as possible. But notice what we also do to it. We multiply it by 2. So we would be interested in a 2 times log likelihood function as large as possible. But then we take it times -2. So instead of looking at as large as possible, now what we want to do is look at -2 times the log likelihood function that's as small as possible. That corresponds to the best model. Now, an unfortunate characteristics then with these log likelihood functions, or likelihood functions in general, is that as you keep on making your model more complicated, meaning that you add more parameters to your model, and this holds true even outside of time series analysis, your log likelihood function will tend to get greater and greater and greater, even if that complexity to your model, these additional parameters, are really not needed. And so one could start throwing stuff in the model and keep on having that log likelihood function to increase, even if it's not necessary, even though it's not really providing a better fit. So because of that, then, we add to the -2 log likelihood function a penalty. We take 2 times the number of parameters that we're estimating. So if you're estimating too many parameters to try to make that log likelihood function even greater, this is going to correct for that. Because now, since I'm adding to it, it's going to increase the -2 log likelihood and thus increase the overall AIC. So that in the end, the model that's the best leads to the largest log likelihood function, but is still as small as possible. And that corresponds to the AIC that is the smallest, the model that has the AIC that's the smallest. Okay. Now, a little note here. I always bring this up whenever I teach an AIC in a course. AICs can be calculated in a different manner across the different software packages, or even across different packages within inside of R itself. And as long as you look at, let's say, an AIC within the same R package, or calculated by the same R package, choose the model that has the lowest AIC, you'll be fine. But let's say you wanted to replicate your results in another R package or even another statistical software package, and you'll still, in that other software package or other R package, that same model should still be chosen, but the AIC value itself may be different. The reason is because there are numerical constants in that likelihood function that are not going to change from one model to the next. So some packages will actually drop those constants, and so that in the end they're not actually using the log likelihood function itself, but actually something that's proportional to what the log likelihood function is. So you might be wondering, well, what are these constants? Well, think of back to when we had the likelihood function previously for our time series models. You might remember there's a 1 over the square root of 2 pi in it from the normal distribution. Well, that's not going to change from one model to the next, or from one set of parameters to the next. That's a constant. And so some packages may simply say, okay, let's just remove that because we don't need that. that's what will cause then the AIC to be calculated different. So just a little bit of a warning here in case you run across this. Now, another thing that you could do, and this is a great idea, and that is to evaluate between different models. Look at the forecast error. Ideally what you would like to be able to do is if I do have a sample size of 100, maybe somehow I could go into the future and get, let's say, the next 10 values for what would happen for this real life situation and compare it to what my model, based upon the first 100 observations, actually forecasted those 10 to be. Then what you could do is find a measure of squared error. So take your observed values, subtract off the predicted value, square it, divide by 10 to get like an average overall value. This would be like a mean square error. And use that, calculate that measure for one model, for another model, for another model, and the model that would be best leads to the smallest average squared error. That ideally is a way we would really like to evaluate our models, because we're doing time series analysis so we can forecast the future. So you could do that here. So what you could do is base your model instead of on n observations, let's say n minus c observations in terms of doing the modeling process. Then with those c observations, these would be the last c observations in your observed time series. So for example, let's say that you do actually observe 110 data points, so time t equal 1 to 110. Just base your modeling based upon the first 100. Save those 10 for later so you can calculate the forecast error, and then the average forecast error across all those 10 for the different models. So you could do that. The problem, though, is that now you're no longer using all your observations to build your model. And especially in a time series situation where you're often most interested in on that first time point after your observed value, you would think that, well, the most previous observed value, so in other words, let's say you're really interested in time 101, well, that time point 100 is going to play a big role in what 101 should be. But instead, if you chopped off, let's say, the last 10 of the series and base your model on modeling t equal 1 through 90, now you're using t equal 90 to help predict 101. That wouldn't be an ideal thing. So that's why I don't usually focus on talking about using forecast error as a way to choose between different models. Okay, so let's go back to this AR1 example. Now, moving average 1 did not pass our issues or diagnostics, so normally I would not consider the moving average 1 here for this particular example. I might consider trying other models with it to see if I can make it better. In the end, I did not do it here. I will in another example later on where I do stuff like that. But anyway, what I'm trying to get at is I'm going to show you what happens with a moving average 1 in step number 5, even though I normally would not. Okay. So in the output, when you actually estimate your model, you will actually see AIC listed in it. Now, you can also pull out the AIC from the model fitting object that's produced by ARIMA. And so for my AR1 model, I get an AIC of 319.363. Again, remember how it's calculated. It's -2 times the log likelihood function plus 2 times your number of parameters that you're estimating your model. So just to verify that indeed that R did do the calculation right, let's take -2 times. I can pull my log likelihood function out. That's evaluated the parameter estimates from mod.fit1 plus my 2 times the number of parameters I'm estimating, which is 3. Why is it 3? You got phi1, you got mu, you got sigma squared w. And look at how it's exactly the same as what we got with the AR1 model. Now for the MA1 model, that AIC is 335. So using this criteria alone, definitely the AR1 model is better than the moving average model because the AIC is smaller. Okay, so that was step 5. Step 6, hey, let's begin forecasting. It's not really part of the model building process, but I like to put that there as actually part of the model building process to emphasize what we are doing or the purpose of time series analysis so that we can forecast the future. And so once you find one overall model, in this case an AR1 model, now let's use it. Let's forecast with it. Okay, so that goes through now the 6 steps of the model building process.